Hello friends, so we'll continue our discussion related to KVL and KCL application in circuits involving dependent sources. So this is another circuit that we have, and here we have been asked to find the voltages Vx and Vy. So see, here in this circuit we have dependent sources. First is this, the voltage dependent current source 1/6 Vi, and then we have the voltage across this current source. Again, it is very important concept, we'll come to it. And we have Vy, the voltage drop across this 3 ohm resistor. So we have been asked to find these two voltage drops. So let us redraw the circuit. So we have this, okay, this is 1/6 Vi. Okay, yes, this is 2 ampere, this is 6 ohm, this is 3 ohm. Now this is plus minus Vx, this is plus minus Vy. Okay. Now one thing, you can never say that the voltage across a current source is 0. Most of the time what happens is that when it comes to a circuit, we are never asked questions like that, but most of the time when you are new to this network theory or circuit theory, what we do or what we think, that the voltage across this current source, we are never asked questions like this. Let's say we have a current source, independent current source or dependent current source, whatever it is. The voltage drop across, or the voltage across this current source, okay, Vi, that is most of the time when you are a new student or understanding, getting started with this network theory or circuit theory, most of the students think that it is 0. So it is wrong. There is some finite voltage across this current source. Why we do this? Because we are never asked we never ask such type of questions. It is very rare you will find. Similarly, the current flowing away or the current supplied by a voltage source, this, okay, when there is different kind of circuit arrangement, this thing, the current supplied or absorbed, if it is flowing in the opposite direction, then the current supplied or absorbed by a voltage source. These two things are very important. So here it is the voltage across this 2 ampere current source, that is Vx. So it means here this voltage is equal to Vx in between this point and ground. So it means technically the voltage at this node is also Vx. That is very important to recognize here and understand and point it out. Now this current, let's say this current is flowing downwards, let's call it I. Let's call this current I. This current flowing downwards is equal to I is equal to Vx minus V ground by 6 plus 3 ohm. This is 0 volt, so that is equal to Vx by 9. I is equal to Vx by 9. Vy is the voltage drop across this 3 ohm resistor, which is equal to 3 into I. Current I is flowing through this 6 ohm and 3 ohm branch. Voltage drop across this 3 ohm is equal to 3 multiplied with the current. That is equal to 3 into I is equal to Vx by 9 which is equal to Vx by 3. That is another important relationship. Vy is equal to Vx by 3. This is another very important relationship which will be used in this circuit. So this is the first, this is the second equation. Now we can apply KCL here, Kirchhoff's current law at this node Vx. So the KCL equation at node Vx can be written as 2 ampere and 1 by 6 Vi. Okay, they are flowing into the node. Okay, 2 ampere and 1 by 6 Vy. This is 2 ampere, this is Vy by 6. They are flowing into the node. So they will be on one side 2 plus Vy by 6, and this current I, that is Vx by 9, is flowing downwards away from the node. So that will be on the other side, Vx by 9. So now let us bring this total equation in terms of Vx by substituting this Vy with Vx by 3. That implies 2 plus Vy with Vx by 3, Vx by 3 by 6 is equal to Vx by 9. That implies 2 plus Vx by 18 is equal to Vx by 9. That implies 2 is equal to Vx by 9 minus Vx by 18, which is equal to 18 2Vx minus Vx, that is equal to 2. That implies Vx is equal to 36 volt. So we got Vx is equal to 36 volt, and Vy is equal to Vx by 3, that is equal to 36 by 3, that is equal to 12 volt. Vy is equal to 12 volt. So we have got the two results that we wanted. Okay, Vx is equal to 36 volt, Vy is equal to 12 volt. So here again the important thing is to identify what kind of dependent sources are there. This is a voltage dependent current source. It is dependent on this parameter, this voltage drop. So first you have to be very clear about the basic application of Kirchhoff's laws. This question was based on Kirchhoff's current law. So we applied Kirchhoff's current law at this node. Okay. Then another thing, to understand the relationship between the dependent parameters. Here we have this voltage dependent current source. It is dependent on this voltage Vy, and this voltage Vy is dependent on this node voltage as per this relationship. So it is very important to identify these relationships. Why? Because we want to bring the equation in terms of one parameter. Suppose here I brought this equation in terms of Vx. If you want, you can also write it in terms of Vy. You would have got Vy is equal to 12 volt. Then you would have got Vx is equal to 3 Vy, but that is equal to 3 into 12, 36. Either way it would have been correct. But you have to know these relationships to bring the equation in terms of one parameter. Only then you can solve it. Another important thing to understand this here. Here the voltage across this current source is Vx. It is important to understand that this node voltage will also be equal to Vx, because this voltage is in between this point and ground, this node and ground. As these two points are shorted together, so these node is 1. The voltage is Vx. Okay, so this is basic application of KCL, basic understanding of circuits involving dependent sources, and this basic behavior of voltage and current sources. we use those things and we solve the circuit. Okay. Hello friends, so here we are with another question on Kirchhoff's law applied to circuits involving dependent sources. So here we have this circuit, simple looking circuit, and we have been asked to find the value of this current I1 and the power dissipated in this 500 ohm resistor. Okay, so for that let us redraw the circuit again. So this is 50 volt, 300 ohm, this is I1, this is 500 ohm, and this is 0.4 I1. Okay, so here our first objective is to find this current I1 and then the power dissipated by the 500 ohm resistor. So for that we have to find the current flowing through this 500 ohm resistor. So here at this node we will apply KCL. Here the current flow is I1 up to this node. Then 0.4 I1 goes into this. So obviously the current flowing through this 500 ohm resistor will be 1 minus 0.4, that is 0.6 I1. This current flowing through the 500 ohm resistor. Polarity will be like this. Current always flows from positive to negative like this. So now we will apply KVL in this closed loop, the left hand side. So the KVL equation will be (50 minus 300 I1 minus 500 into 0.6 I1 is equal to 0. This. That implies 50 minus 300 I1 minus 500 into 0.6, that is equal to 50 into 6, that is again this is also 300 I1 is equal to 0. That implies 50 minus 600 I1 is equal to 0. That implies I1 is equal to 50 by 600, that is equal to 0.083 ampere. Okay, this is I1. We have got the first thing that was asked, 0.083 ampere. Then we have to find out the power dissipated through this 500 ohm resistor. So we know the power dissipated through a resistor is basically I square R, V into I, which is equal to I square R. It can also be V square by R, anything. So here we'll be using this I square R thing. So here it will be power dissipated in the 500 ohm resistor is equal to current flowing through it, that is 0.6 I1 I square into 500. So it will be 0.6 into 0.083 whole square into 500, because I1 is equal to this we calculated. So let us calculate how much it is coming. 0.6 into 0.083 whole square into 500. So it is coming around 1.24 watts. Okay, this is the power dissipated, 500 ohm resistor. this. Okay, so again this is a very basic circuit, simple circuit with simple understanding of KVL and KCL. Okay, we applied KCL here to get the current flowing through the 500 ohm resistor. Then we applied KVL in this left loop to get the value of I1. We then used this I1 to find the power dissipated in the 500 ohm resistor. Okay.